Get in the habit of doing it. Yeah. I may give you a little slack in terms of what happens in lecture, but I definitely will count off for it in lab. So you might as well just get used to it, and that way you don't have to. Okay, one of the last topics here, density. This will be useful. This will be our second lab that we do. We'll be doing a density analysis. It's pretty straightforward. Density. What density is a ratio of the mass of something to the amount of volume that it occupies. And what that means to you is it's important in identifying something. For example, the density of, the density of liquid water at 4 degrees Celsius. Okay? The density of water means that if I have 1 gram of water and I put it on a scale, if I have 1 milliliter of water, I measure it out, 1 mil, put it on a scale and weigh it, it's going to weigh 1 gram. That's what water is. Water has a density of 1. What that means is the ratio, in other words, the fraction, if you put the mass on top and the volume on bottom of any situation, it will remain constant. For example, if I have 1 milliliter of water, I put it on a scale, it's going to weigh 1 gram. If I have 2 milliliters of water and I put it on a scale, guess how much it's going to weigh? 2 grams. If I have 100 milliliters of water, it's going to weigh 100 grams. Every time I take the gram value and divide it by the milliliter value, I get the same number. That's the density of water. That's the ratio of its mass to its volume, always. And you will find that all these things out there have their own unique density. It's sort of like their own little fingerprint. There's a whole lot more in terms of fingerprinting things, and I'll talk about that, especially when we get into electrons and atoms. It'll blow your mind. Okay? So let's consider this. Mass and volume themselves are the two main characteristics of matter. Okay? Consider this. I can't necessarily use it to determine what type of matter something is, but it can certainly describe the situation in which I find myself in terms of how this seems to be behaving. It'll lead to help us identify something. For example, if you are given a large glass containing 100 grams of a clear, colorless liquid, and a small glass containing 25 grams of a clear, colorless liquid, are both liquids the same stuff? Well, you don't know by looking. There certainly are a lot of chemical tests that we could do, but what's something very simple that we can do? We can take a given mass of it, take a given volume of it, and then weigh it, or mass it, I guess, on a scale, and see what the ratio is. Do the same thing for the other substance and see if that ratio is the same. It shouldn't matter what volume I pick, because what you'll see is the weight will increase proportionally to the volume that I put on there. So this is one way to see if two things are the same, made of the same material, for example. You'll see a Greek philosopher came up with, Archimedes actually, but came up with a really interesting scenario for a king a couple thousand years ago. I'll talk about it here in a second. So the mass and the volume are certainly related to each other. Okay. By the way, if you ever wonder how these giant aircraft carriers, right? These ginormous ships that are out there, how in the world do they stay above water? Because you know that if you took a steel ball that only weighed, I don't know, a fraction of a pound, and I dropped it in water, it's going to sink straight to the bottom, right? Why can I take these massively huge ships, put them on water, and why in the world do they float? You ever really think about that? Surface tension and buoyancy certainly have a lot to do with it. It has to do with playing with this ratio of mass and volume. Okay, the bigger you make this boat, the more you spread it out, what you do is you increase its volume, right? I could take all the metal that was in one of these boats, and I could compress it all down and make this dense like cube or ball. I drop that in the ocean, it's going straight down. But if I spread it all out and I pull this metal out and make it take up a bigger area, you know that density is mass over volume. I'll show you this equation in a second. It's mass divided by volume. The mass hasn't changed, whether or not it's this big or whether it's as big as this room. The mass is going to be the same. It's the same amount of matter that's present. What have you done? You have changed the total, the volume that mass occupies is what you've done. You spread it all out. So what does that do to the ratio? That denominator, what happens to it, right? That denominator gets bigger and bigger and bigger. What happens when a denominator gets bigger? Does the number get bigger or smaller? it gets smaller, right? The smaller it gets, that's the goal. Because when you mix two things together, whichever one is more dense than the other is going to stay underneath. Whichever one is less dense is going to float on top of the other substance. So you can create something like a large ship, for example, manipulate its volume that it takes up, so that when you divide the mass by the volume, you actually get a number that could be less than the density of water, let's say. That's not completely true, but for my point of illustration, you get the concept. Okay, there's some other things I would have to explain in terms of physics for that, but you can see how you can manipulate that to a benefit. It's sort of a, you ever notice too, anybody ever go to a family reunion? And, you know, down where I'm from, that's what you do. You go to family reunions, and it's the same crap every year. You know, the same people bring the same thing and set in the same places. Potato salad, big tub of pop. Next time you're at this big tub of pop, if you got a big one, and it's good and cold with ice water, not a whole lot of ice in there, but it's just good and cold with the cold water now, look and see, especially if there's not a whole lot of stuff in there, compare in this giant tub where the diet pop is versus where the regular pop is. Diet pop is actually a little bit less dense than water. It will float in water. Regular pop will sink in water. There's a little bit of a density difference between the two. Now, it's not completely obvious. What you can do is if you go slow, like if I do a demonstration for one of the lab videos that I made here. If I have two big containers and I let go of them very easily at the same time, the regular Coke will sink straight to the bottom. The diet pop will just sort of float right underneath the surface. Not all the way at the top, but right near the surface. You can start seeing this if you pay attention. These are just some things that you might pick up on. All right. So here's an example, an illustration. Let's say we have brass. Brass is an alloy made of zinc and copper. Okay? We'll talk about those type of things later in the semester. But if I have certain samples of brass, and let's say they're cubes, because cubic centimeters, that way they're easy to measure. I can calculate the volume very easily. Say I have different cubes of brass. And I have a 2.4 cubic centimeter size of a block. I mass it. It weighs 20 grams. I get a bigger hunk of this same sample of brass, and it's compress it into a 3.8 cubic centimeter block. I find that it weighs 32 grams, and so on and so forth. Okay? Notice what is happening. I'm increasing the volume. Notice what else is happening. The mass naturally increases the more of it that I have. My point is, what I want you to see with density is that there is a number that is constant. It increases by the same factor every single time. Because what happens is, if you plot that, you should have made graphs before. If you take, like in this case, notice the volume here at the bottom on your x-axis and mass on your y-axis. So if you use these numbers, you put this along your x-axis, put this up your y-axis, and meet the points and make a line graph, or just connect the dots, and then with a line, it ends up being a straight line. What you will see is that it forms a really nice line. It's a linear proportion. Whenever the volume goes up, so does the mass, and they happen to go up in a very linear fashion by the same to the same degree every single time, the same relationship. So as if you took this number, whatever this mass was at this point right here, and divided it by the volume, and you did the same thing here and the same thing here, you would constantly get the same answer over and over and over. That's the density of that object. So, D is equal to M over V. Density is mass divided by volume. You'll need to know that. The way that we express this in terms of solids is to use cubic centimeters. Because milliliters, you usually use that for liquids, right? It's not very handy in terms of when we're dealing with solid material. So one way to measure volume is like length times width times height, which would be like a distance measurement, like centimeters, meters, whatever. So one way that you measure solids is grams per cubic centimeter. Like I did with that brass thing. You can measure the volume in cubic centimeters, put it on a balance, get a gram value. Now, one thing you might want to know, depending on what field you work in and what things you've heard and what TV shows you've watched. 1 cubic centimeter, that's what a cc stands for. Okay? 1 cc is 1 cubic centimeter. Now, also, when we're dealing with most liquids, you can assume that from here on out, but it's not always true, but we'll assume it for now. We're going to say that 1 cubic centimeter is equal to 1 cc because they're the same thing, but that is the same as a milliliter. as well. So if I have 30 cc's of water, I have 30 milliliters of water.